So in this tutorial, we are gonna learn about r squared, or the coefficient of determination. Basically, we will dig deeper into the physical meaning, or what does it mean by r squared. So first, we need to know like why r squared is required, or why actually it is required. R squared is something that we need in case of regression. For example, in this picture or in this plot, we have a case where we have a linear regression. So if we explain it step by step, we have the actual data, or the observed data, that is represented by these blue markers, and we denote it through y. I here is the iterations, because we have I number of data point, and we have a straight line that is predicting this data point. This red straight line is represented by y hat, and we have a mean value, which is y bar, and this y bar is nothing but the average of all these actual data point. Now, the main purpose of this linear regression here in this plot is to predict all these data points, so that if there is a random value of x, we can predict the value of what would be the value of y, even though that is not observed, or we haven't received data for that particular x. So the whole purpose of this linear regression would be to make this fit perfect, or like near perfect. So the how good is the fit, that is actually represented by r squared. So the purpose of r squared is nothing but just to make sure, or just as a checking of the fitting of this line with this data point. However, like, we would like to know more about r squared, like why or what actually what actually is meant by this term, or well, actually the significance of this. So for this, we'll have to first understand a few things. We need to know that in this whole problem, we have three kind of variabilities. The first variability is called the SST, or total sum of squares, which is nothing but the total variation of these data points, actual data points. So in our in our case, if we see our value marked by the blue cross markers varies from 5 to 35, and this variability or variation is something that we would want to measure, because this is really important. Say we have our straight line that we want to uh, use as a fit. We need to know that how much variation it's taking place, so that we can know the slope of this straight line, and like how it should be oriented. So it's really important to know what is the total variation, and that is something that the variation of the actual data is measured in terms of the mean value of this of the data points, the which is represented by y bar. So for that, we basically take the mean for all these data point, and we take the average. So here it SST shows the variation of this data point, which we measure by taking the difference of each of these data point from the mean value, and taking adding them, like squaring them, and summing them up. Now next step, we would want to use this value as a reference to to draw our straight line, which is marked by this red prediction line. Uh, so for that, we need to first we need to consider the fact that this variability in the actual data has to be captured by this straight line. So in this process, we try to fit it, and then we kind of check how much our prediction line has been able to capture this variability. And that is represented by the next variability term, which is called SSR, or sum of squares for regression. The portion of total variability that can be explained by the model. So just consider a case where our prediction line has been able, or our prediction plot has been able to predict, or has been able to capture all the variability of our actual data. In that case, SSR is gonna be same as SST. Why? Because the actual value would be same as the predicted value. However, in real case, that's not possible in most of the cases, because there will always be an error. Our model or our prediction line will not be able to capture the variability completely, and that difference, that portion, what our prediction line is unable to capture, that portion of variability is called sum of squared for error, or SSE. So yeah, by definition, this is the portion of total variability, or SST. This is just SST, is T, that cannot be explained by the model. So this is, as I said, if these two terms uh, how different are these two terms, or the two values, the prediction value and the actual value, is basically the measurement of the SSE, or the sum of squares for error. And from the definition, we can understand that SST, or the total sum of square, is actually the summation of these two. Now this equation is really important for the foundation of R squared. Now, as I said, like, R squared here is nothing but it kind of relates all of these three terms. Like the physical explanation that I provided is just represented mathematically through R squared. So R squared is SSR over SST, which is the variability of data captured by the model by the variability of the actual data. So it means R square basically means how good our linear fit, or our linear prediction line has been able to capture the variability of the actual data set Y. So if it's able to completely capture the variability of Y, SST will be equal to SSR, because these two equations, from equation 1 and equation 2, let me just bring my laser so that it becomes easy to understand. So R squared will be 1, and when R squared will be 1, it means that our prediction line has been able to completely able to capture the variability of the original data set Y. So it means that our prediction line kind of like totally fits the actual value, meaning that y would be equal to y hat. And that means these two equations, equation 1 and 2, will be same. So SST will be SSR and R squared will be 1. That means the best fit, or like we cannot get a better fit than that. And what does R squared is equal to 0 mean? So R squared is equal to 0 means that our prediction line hasn't been able to capture the variability of the actual data at all. So that means our y hat is way off than the actual value y, and that's why these two terms are very different. So there is a quite a bit difference, and this difference is represented by SSE. So SSE is nothing but the difference, between this the actual value and the predicted value, which is causing the error, or which is causing our model not to predict the actual data properly. So we can express this thing, or the relation between the SSE and R squared through this equation. This is nothing but just we have derived using, let me bring my, we have derived it based by manipulating these two equations. And this equation is also really important. It means that when we have 100% error, say our model hasn't been able to predict the data at all, and then like this is gonna be like there will be like SSR, which is gonna be 0, because it hasn't been able to capture our model, or the straight line, the linear regression line hasn't been able to capture the variability at all. That means SSE is equal to SSE is gonna be SST, and so it's gonna be 1 minus 0. Sorry, it's gonna be 1 minus 1. It's gonna be 1 minus 1, which is gonna be 0, which means this is a really bad fit. Our regression line hasn't been able to represent the actual data at all. This is gonna be 0 in that case. And R squared is gonna be 0 as well. The R squared is gonna be 0. Now the next thing is what if there is no error at all? Say our data completely our regression line, or our model completely capture the variability in the actual data. Then we say that y is equal to y hat, and then there is no SSE. So SSE in that case will be 0. So our regression R squared will be 1. And here, from here, we can also see that SSR and SST is gonna be equal, so R squared is gonna be 1. So for best fit, R squared is gonna be 1, and that can be explained in terms of all of these terms. So yeah, so that is basically the meaning, the physical meaning of R squared. And another thing that is really important to consider is that we don't, even though 1 means that, so as I said that the value of R squares actually varies from 0 to 1. So 1 means this is the best fit, or the fit is really good, but it's not actually true for all the case, because we don't want the regression line to fit 100% to our data, because oftentimes it leads to overfitting, because it kind of like, say if our regression line used to fit all of this data like this is not gonna be a linear fit at all. then it's gonna be a polynomial fit in that case. So probably gonna work pretty well with this data set or with this training data set. But when we will have a test data, so say we have a random data coming from an outside this data set, this is not gonna be able to predict this properly. Like it's even though it's 100% fitting with the training data, is showing that r squared is showing like really good fit, like r squared is equal to 1. When we put a training data, as it's not gonna be able to capture this data that with that precision, with the training data, the r squared value will be lower. So that's why we want some sort of optimization. Ideally, we are happy if our value of r squared is 0.94 or 9596 in this range. Now, another thing is also like another interesting case is say our linear fit. This is now going like really through the data set, but it could also happen. It could also happen that the linear prediction line was way off, so it went through this line like way up above or way below. So this basically means that the let me wonder, yeah. So this is our linear line, and this means that this line hasn't been able to capture our data or the variability of our data at all. So in that case, what will actually happen? There can be some sort of confusion that may happen, but through the value of r squared, how that's what I wanted to just show. For example, in this position, if we see there is quite a this can be if we calculate the SSR, because like from the previous discussion we know that we want r squared value to be high. So from this equation we want, so it is good that if SSR is bigger, that's good for us, and if SST is smaller, that's good as well. So that's the condition that we want. But when we have with this new position of this linear prediction line, our SSR value will be quite high. So y hat, which is represented by this line, minus our average value. So this average line is dependent on this actual data. So this actual data is not changing. So this line, this green line's position is not changing at all. But as we move it up, so we consider this distance to be like extremely high. So say h tends to infinite. So if this is quite high, so we can see that we can actually make the SSR to be like infinitely high. But our value of SST in this case is not gonna be varying, because it's not a function of the linear fit. It's totally independent on the actual data set. It's never actually gonna change. So but from our r squared equation, if we have a look, we will see that this would seem to have a value that is really high, that is not 1, that's over 1, because our SSR's value is way higher than SST. SST is not changing, but SSR is highly increased because of moving this straight line far higher. So these kind of cases indicate that we have a very poor fit. So by seeing the value of r squared, we can also see that this is a very poor fit. How there is another way of mathematically evaluating it, that this fit is poor, through this line, through this equation, this alternative equation of r squared. Because when SSR is going to be significantly higher, Interestingly, the value of SSE is it's gonna be high as well, because the error of our actual data point is this one, and our prediction data point is this one. The difference between this is represented by SSE, and this is not gonna be minimal. This is actually gonna increase as this line moves up. This line moves up. So that means this SSE is gonna be highly increased compared to SST. So this means that R squared in the second equation is gonna appear as negative, where R squared for the same case in this equation is gonna be more than 1. It's gonna be negative here. So that kind of indicates that our fit is very poor. So to summarize, R squared is nothing but a way of like this kind of means how good is our fit. In more detail, how good our prediction line has been able to capture the variability of the actual data set. So if it is able to 100% capture the variability of the data set, there will be minimal error, and the value of SSE would be close to 0. And we also want to have the value of R squared to be between 0 and 1. We never want this to be to go beyond 1, which is physically impossible, and we don't want it to be closer to 0. So the whole purpose of the fitting or using any algorithm to optimize our prediction line is to make sure that our R squared value is close to 1, is very close to 1. And yeah, that's this explanation, or this physical understanding of R squared is really important, at least to remember all these terms, all these works. And these are another way of checking the fit of our regression line. Thank you.